Bismillah ar-Rahman ar-Rahim. All right, class, Assalamu alaikum, and welcome to the third lecture of week 5. And today we are going to discuss about the electric field intensity, uh, which is produced by a collection of charges, different arrangement of charges that can be three-dimensional, one-dimensional, and two-dimensional. So keep referring to that table, the progress table, which we discussed in the last lecture of week 4. So keep referring back to that. So far we have discussed the vector field effect, which belongs to force field kind of vector field effect of a static charge distribution, and that charge distribution was so far zero-dimensional point charge distribution. But before moving on to the other dimensional charge arrangements, static charge arrangements, I would like to discuss about these two terminologies, incremental and differential. Both terms you must have listened somewhere, that these terms are not new for you. However, I want to point out, I want to refresh your memories with the basic concept of this. Both of them are, microscopic entities. Anything which is incremental or differential in nature, let's say differential length or incremental length, or differential surface or incremental surface, differential area, incremental area, differential volume, incremental volume, all these entities which are differential or incremental, they are all microscopic in nature. You cannot be seen from naked eye. Even the person with 6x6 vision cannot watch it, okay, cannot visualize that, cannot see it, can visualize but cannot see it. All right, so but there is a fundamental difference between the two. Both are microscopic, never mind, but there is still a difference between the two. Let's say now, let me give you an example which might not be technically correct, but this example might give you, some sense of what I'm trying to talk about. We all know that if I take a finite length, all right, a finite line segment, this line segment is made up of infinite points, all right, and even in this length, in this short segment, there are infinite number of points, because we know that point is a zero-dimensional entity which has got no height, no width, no depth. So something which has got no height, no width, no depth can never define a length. All right, so never mind how many points I put together, they will never add up to something finite. All right, so 0 plus 0 plus 0 plus 0 plus up till 0 infinity, you will get a 0. So technically it is not correct, but if we consider that a line is made up of several points, placed side by side. Now we are deviating from actual definition of point, but this will, this will aid to your visualization of incremental and differential entities. So let's say we have a finite segment, and I take a very small portion of that finite segment, and let's say I magnify this small segment. So you'll see these two extremities, you'll see here, and let's say the magnification is 1 billionth times. Okay, so I magnified this by 1 billion. Obviously I cannot multiply it by 1 billion times on this same board, but for the sake of argument you can understand it. Now if I take another small segment within this segment, and now if I multiply it by, magnify it by, another trillion times, all right, and what I'll see after this, I see I start to see, the small dots which are, or the pixels if you like, which are making this line segment. And now if I take a small segment here, and then I magnify it by a trillion times once more. So what I'll see, you know, these points which are making. Again, I'm telling you, warning you, this definition is mathematically incorrect, but just to aid you with your visualization. So this line is made up of, you know, several points put together side by side. All right. So what is incremental length? If I say that I want to take incremental length on this macroscopic line, which you can see from your naked eye, I want to choose incremental length on this line. So what I'll say, okay, I'm taking this length, but how long is this length? This length is actually maybe this long, you know, this long. This is that incremental length. 1, 2, 3, approximately 10 points wide. This is this incremental length. But what does it means if I want to take differential length on this line? That means that I'm interested in only one point. This is differential length. Always keep in mind, both are microscopic. So actually I magnified it by billion times, then trillion times, then trillion times, and why not make it trillion times? Okay, trillion times. So after that I was able to see that okay, now this line is made up of, you know, several points, which is again, by the way, mathematically wrong, conceptually wrong, but you can think of it like this. All right. So if you want to take about 10 points probably, or 12 points or 8 points, there is no fixed rule. That length is incremental length. But if you are interested in precisely only one point, then it means that you are interested in a length which is of that particular point. And same can be extended to differential surfaces. Let's say if this was not a line, and let's say it was a surface, okay, and I wanted a patch on this surface area, and if I magnify it by trillion times, what I'll get? I get a bigger patch. I have magnified it by trillion times. And again, now if I on this patch, if I take another patch and then magnify it by trillion times, what I would get is, you know, this time I would get a surface area. Okay, something like this. And now if I take a very small portion of it and then magnify it by a trillion times, what I'll get this picture. So what does it really mean to have an incremental surface? It means that approximately 10 points in this direction and 10 points in vertical direction. That's it. That is differential surface. But if I am interested in, you know, only this patch, so it means that I'm interested in differential surface. If I am interested in 10 points by 10 points, that would be incremental surface. But if I am interested in very small patch with the size, a patch which is itself the size of a point, is the differential surface. I hope I made myself clear explaining the difference between the two. All right, so keep in mind that differential surfaces are always, differential entities are always, you know, equal to the point, are always approaching the point size, and incremental entities, although very small, but never can never be treated as a point, because they are sufficiently larger than a point. So let's say we have a cluster of charges now which occupies some volume, and the distance between each point charge is so small that we cannot measure that distance. Okay, let's say we have this length is, let's say, 1 micrometer, and this length is 1 micrometer. We have no probe whatsoever to measure, you know, the distances between. So and if I want to find, let's say, at some point here, this point, this is my field point where I want to find the electric field intensity. So due to this cluster of charges which is occupying some volume V, so how to proceed in this case? Okay. All right. So for such cases where we cannot find the total charge, what is the solution is that we define charge density in much the same way in which we used to define mass density. If I give you some liquid, and if I give you that liquid in some container and ask you to find you the density, what would you do? You will calculate the mass, you will weight that liquid, okay, and then you will divide that the weight of that, the mass, sorry, not the weight, the mass, you will divide that mass by the volume of the container, and you'll get a constant density. But remember that in that case, in the case of liquid, or in the case of some solid, maybe in the case of water density, what's the presumption? The assumption is that, which is true, that the molecules of that liquid, they are, you know, uniformly distributed throughout the container. They are in, why? Because water or any liquid is considered as an incompressible material, okay, an incompressible matter. So if it is incompressible, it means no matter how much pressure you apply over water, the spacing between the molecules will not change. So what you do, you just take the weight of all the molecules combined together, and then you divide that weight by the volume of the container, and there you go, you get a constant density for that case. But here, you know, the charges are not uniformly distributed throughout that volume. You can see that at some region, in some region the charges are densely populated, and in other region they are sparsely populated, they are not so much densely populated. So definitely we cannot give a density of volumetric charge density or charge density in such cases as a constant quantities. Constant charge densities might be possible, but that can be a special case to this. So we are trying to give the definition of charge density generally. We are not talking about constant charge density. So generally, how would you do it? How would you find the density? What we can do in such cases, that we can you know, take what we can do is that we can take, let's say this red zone as the volume in which the charges are closely packed together, okay, and let's say these points are again charges. So somewhere they are densely populated, and somewhere they are, at some places they are loosely or sparsely populated. All right, never mind, but they are occupying a volume. So what we can do in such cases is that we can take a very small incremental volume. Incremental volume means delta V, not dV, and we can find the charge which is enclosed in this incremental volume, and let's say that incremental charge is represented by delta Q. So if we take the ratio charge per unit volume, this is what, this will almost be equals to the entity which we call rho V, which we represent as rho V, but we call it volumetric charge density. Okay, so this is not exactly equals to, this is, you know, almost equals to. Why? Because this incremental size, if this red box, if I move this box around, this box can occupy one charge within itself, or maybe if I move it somewhere here, it will occupy 4 charges or 3 charges. So in that case, what I'll get, you know, something which is not constant on the right hand side. Okay, so how to make it constant? How to ensure that this box or this volumetric, this volume, incremental volume, occupies exactly one charge in it, or yeah, how to do that? It can only be possible if we apply a limit in this expression, that if we apply a limit that the size of this volume, this box, is so small that it is tending to 0, in that case this ratio, which was previously almost equals to, will become exactly equals to charge density. And when this is so small that it is approaching to a volume 0, or in other words, if it is approaching to a point, we can say that you know, this volume has become from incremental entity to a differential entity, and this differential entity now is occupying a charge which we can refer to as differential charge. So what we have now, this is equals to rho v. Okay, so now volumetric charge density or rho v is nothing but differential amount of charge enclosed in differential amount of volume. If I want to find the total charge, what I can do, I can cross multiply it. This is v, by the way. Okay, this is v, and now in order to find the total charge, what we can do is we can integrate it. Okay, rho v dv, but this integration is a special integration called volumetric integration, or volume integration, meaning because since this is, you know, dv, differential volume, which we talked about while discussing coordinate systems, so there should be 3 variables in it. So integration should be performed by each of, with respect to each of the variables. So this is how we define volume charge densities. So in the same flow, I would like to now define, you know, line charge density. Let's say if we have got an infinite line over which charge are distributed, okay, and that distribution is not necessary that distribution is uniform. So and let's say this line goes up to any indeterminate length or maybe infinite length. How we can find out the charge on this line? For that case as well, because there is uncertainty in measurement of charge, what we can do is define an entity which is known as line charge density, just like we did in the case of volume charge density. We'll define an entity, line charge density, as rho L, and following the same argument that if I divide this, you know, whole length into incremental lengths, so this incremental length will carry a charge which can be represented as incremental charge. So if we take the ratio of incremental entities, we'll almost get, you know, the line charge density. But it might be possible that if I move this incremental element from here to here and measure the value of charge, here the charge density might be lesser or higher than this point. So what will end up in is you know, a fuzzy type of entity which is indeterminate. Here it will give different density, here it will give different density. To be determinate, to be, you know, sure that each incremental length occupies only one point charge, in that case we'll have to apply a limit that the incremental length is so small that it is approaching 0. In that case, this ratio will become exactly equals to, now I have removed the dot on top, so this is how we deal with it. So it means on the right hand side, when we apply this limit, that delta L is so small that it is approaching 0, it means that it is approaching a point length. So delta L is represented by dl now. So this differential length, which is now enclosing or occupy or containing in itself a charge, that charge will be represented by a differential charge dq. So rho v is equals to dq. So rho L, rho L equals to dq. So now if I want to define charge density, line charge density, I can do this. And if I want to find the total charge on a certain length, what I can do, I can multiply it, cross multiply it, and take the integration. Now this integration will be with respect to one variable only, because line charge is a unidimensional charge arrangement. All right, so this is how we do it. So now for a surface charge distribution, following the same argument, we define surface charge density, which is represented by rho s. By the way, the units of rho v is coulombs per meter cube. It's obvious, charge per volume, and rho L is coulombs per meter. So for this, it should be coulombs per meter square, and that should be charge enclosed in a differential amount of charge enclosed in differential amount of surface. Then if I want to find the total charge, what I can do, I can just cross multiply it, rho s ds, and take the integration. Now this time the integration will be this surface integration. So this, here we go, the third formula, which gives us the total charge in terms of several charge densities. So definitely, if we have got a three-dimensional charge distribution, we will be given with rho v, or we'll have to find rho v, and you will have to use this formula to find the total charge in that volume of clustered charges. And let's say if the charge distribution is one-dimensional charge distribution, meaning that charge is in the form of a line or a curve, in that case we'll be given with rho L, line charge density, or we'll have to find rho L. And after having this rho L, that is the line charge density, if you want to find the total charges occupied in a certain length, we can use this formula to find that, and same argument goes for. So for two-dimensional charge distribution, we need to have surface charge density, and after having surface charge density, what we can have the total charge on a specified surface area. All right, so now having described all the three charge densities, now let's come back to the problem that if we have got this kind of arrangement of charges, how can we find the electric field intensity at this point? And let's say we define that origin is here. This is origin. Okay, so now we knew from our previous class that electric field intensity due to a point charge whose value is q is given by this expression. We have derived this in the last class. So let's say if I divide this whole volume, macroscopic volume, into our microscopic volume into very small, meaning differential volumes. If I divide it in differential volumes, so in each differential volume there will be some differential charge stored. So that charge can be treated as a point charge. All right, so to locate that point charge, what we can do, we can use a position vector starting from origin, ending at this differential length, differential volume, which stores that differential point charge. And we know that this position vector is nothing but small r prime, and the position vector which locates the field point is given by position vector r. We all know that. So what we need to find is this vector which starts from the source and terminates at the field point, and that is r minus r prime. Okay, so this is r minus, if this is r minus r prime, meaning this distance between the source point and the field point, this is r minus r prime, and its magnitude will be at the denominator. So this was the general formula, but in our case this formula will be modified a little bit, that instead of q, now that point charge is given by dq. So dq is here, rest is the same. So the differential amount of charge will produce the differential field contribution, differential contribution of the field, because the total field at this point will be from differential contributions of field from each of the point charge here. So let's say this differential point charge is contributing differentially to that field, to the total field. So that differential field is given by this dE. All right, so we can replace this dq by rho dV, because we know that this is the relationship. All right, so to get the total field, at this point, what we need to have, we need to add up the contribution of all differential fields due to each and every point charge. और if I can say that, अगर मैं इसको divide कर दूं बहुत छोटे-छोटे differential volumes के अंदर, so I'll have infinite volumes in this direction, and also in depth. All right, so if I add up all those incremental contributions due to each of those incremental volumes, differential volumes, what I'll have to do, I'll have to integrate this expression and get this final result. Remember that this integration is volumetric integration. So this is how we find electric field intensity in case of a volumetric charge distribution. All right, so now we have seen the field due to zero-dimensional point charges, zero-dimensional cluster of finite arrangement of point charges, and three-dimensional volume charge distribution, how to find electric field, the formula actually. So now we are moving on to the one-dimensional charge distribution. That, let's say we have got an infinite line charge, this is infinite. All right, so, and which is given by a constant charge distribution. So we are not only considering a line charge which is infinite, but also we are considering a line charge which is uniform line charge, meaning that no matter if I measure charge in this segment delta L, or in this segment, or anywhere on this line, I'll get the same value of Q. So this is a relatively special case. So never mind. So now we are given with this infinite line charge. So first thing first, we have to consider that which coordinate system we should use in order to find the electric field intensity. Remember that at the end of the last class, I showed you with a very simple example that, let's say we have a point charge, and how we want to write a field of that point charge. So if we had if we were clever with our approach, and if we had used the spherical coordinate system, the expression for electric field intensity would have been very easy. And if we had used the rectangular coordinate system, we will somehow get the electric field in that case as well, but the expression will be very formidable, very complex, and may intimidate you. So now in this case, we have to choose the coordinate system which we should use to establish a formula for electric field intensity of such one-dimensional charge distribution, or source distribution, if I can say. So how to choose it? So for this, we need to do some symmetry checks. Okay, symmetry checks have got only two clauses. Clause number one, that we have to find the coordinates for which the magnitude is important. The magnitude of field is expected to change Okay, so magnitude is important. Number 2, which components of the field would exist? Seems difficult. Let me explain it. Okay, so what it actually means to do the symmetry check. All right, to do the symmetry check, what we have to do, we have to evaluate the symmetry of the charge distribution itself and see that if the magnitude is changing or not. Let's see how exactly. So we have got three options: either to use Cartesian coordinate system, in which these are the coordinate values and these are the unit vectors. Okay, so electric field intensity will have x component, y component and a z component, is it? And this option number 2 is to use cylindrical coordinate system, in which we have got these values, these coordinates, and we have got these unit vectors. So what we should expect? We should expect a formula for electric field like this. Okay, and option number 3 is we use spherical coordinate system, in which we have got the coordinates r, theta and phi, or the variables r, theta and phi, and primitive unit vectors are theta, phi, r. And if we choose to represent the field in this coordinate system, then we should have some r component, some theta component and some phi component. That's it. Okay, so which one to choose? Which one to choose to, to find the final expression of E? This one, or this one? Clause number 1. The coordinate for which the magnitude of the field is expected to change. So if you think of this line charge as a tube light, okay, as a tube light. All right, so and let's say we put that tube light on z-axis. This is infinite tube light, several thousand tube lights joined together in order to make one infinite tube light. And that when that tube light is turned on, meaning we have to see that changing which coordinate will change the magnitude of that intensity. If you are talking about the tube light, then light intensity should be the thing which we should be interested in. So that will be analogous to electric field intensity. Okay, अगर हम ये तस्वीर करें कि इलेक्ट्रिक फील्ड इंटेंसिटी की जो इस लाइन चार्ज, इनफाइनाइट लाइन चार्ज की जो इलेक्ट्रिक फील्ड इंटेंसिटी बन रही होगी, वो उसी तरह की होगी जिस तरह की कोई ट्यूबलाइट अगर हो, इनफाइनाइट ट्यूबलाइट, उसकी जो लाइट इंटेंसिटी होगी. ऑलराइट, बिकॉज लाइट इज समथिंग which can be sensed by our eyes. Electric field intensity is something which cannot be measured or sensed by our eyes. So अगर हमारी आंखें इलेक्ट्रिक फील्ड इंटेंसिटी देख सकती होती तो ये लाइन चार्ज अरेंजमेंट उसको एक ट्यूबलाइट की तरह ही नजर आती, लेकिन क्योंकि हम इलेक्ट्रिक फील्ड देख नहीं सकते, इसलिए हम बेहतर ये है कि हम इसको समझेंगे ट्यूबलाइट है. ओके, नाउ इफ वी चूज दिस, ओके, सो if this is z-axis, okay, now if I establish the other two coordinates, so it will be x and it will be y, is it? Okay, x and y. So if I change x, meaning I am moving along this, or if I change y, meaning I am moving along this direction, so if I change x and if I change y, obviously my distance from the source will change, so the light intensity which I will be experiencing will change. The coordinate for which the magnitude of the field is expected to change if we choose this, if we choose to work in a Cartesian coordinate system, changing x and changing y will definitely change the magnitude of the field. Okay, that field can be electric field or magnetic field, or light field in our case. Okay, so if I change z only, keeping x and y constant, so I will be moving along this line charge or this tube light, so my distance will be same. So if I move, if I change, if I'm at this point and I change only the z coordinate, I will move parallel to the source, so magnitude of the field is not expected to change. Okay, all right, so how about if we use cylindrical coordinate system. In cylindrical coordinate system, if I am at this point, let's say, meaning I am on a cylinder, and if I changed only this, keeping these two constant, so meaning that I am moving in this direction. If I increase this, I will move away of the z-axis, and if I decrease this, I will move towards z-axis. It means that I am moving away or closer to the source. If I change this coordinate, it means that it is expected that changing this coordinate will result in change in the magnitude of the field, which in our case is intensity of that tube light. How about phi? If I am at this point, okay, if I am at this point, I change phi means अगर मैं इसको ऊपर से दिखाऊं टॉप से, this line charge will be this point, okay, and this will be the y-axis and this will be the x-axis, okay, minus y-axis minus x-axis. Now I am at this point, and now I want to change only phi and see that whether the magnitude is expected to change or not. So when I am here moving along the phi direction means that I will move in a circle. So if keeping rho constant and z constant, if I move in a circle, the circle which is on z equals 0 plane, if I keep on moving, it means that मैं उस light का तवाफ कर रहा हूँ एक तरह से. Okay, I am just revolving around that light, meaning that the distance won't change. It means that if I change phi, magnitude of field is not expected to change, because distance with respect to the source is not being changing. So, and since we have defined z in the board coordinate system similarly, in the similar fashion, so changing the value of z will not change the field, the magnitude of the field, or because the distance with the source will not change. How about if we work in a spherical coordinate system? If I am at this point, okay, or this point, what is r? R is the distance of this point to the origin. Okay, this is r. So if I change r means I either move in this direction or this direction. It means I'm going towards the source or away of the source. So obviously changing r will bring me closer or away of the source, meaning that the magnitude of the field is expected to change. अगर मैं ट्यूबलाइट के करीब आ जाऊंगा या उससे दूर चला जाऊंगा तो obviously उस लाइट की शिद्दत मुझे कम या ज़्यादा महसूस होगी. Similarly, theta, changing theta means that keeping now r and phi constant, changing theta means now if I am at, let's say, this point, I was at this point, if I move along this arc, I am on the same spherical surface, all right, and I am on the same radial plane, meaning if I drop perpendicular from here to here, both will make a constant angle. Okay, so never mind, coming from here to here is changing is not changing my distance from origin, but it is changing my distance from the source. Earlier I was closer, now I am a little farther. Okay, if this is the line charge and I am standing here or I am standing here, you know, there will be a change in the distance from the field point and the source point. It means that changing theta will definitely change the value of phi, a value of magnitude of field. And since phi is defined as the same way, so we can say that, okay, phi, changing the value of phi will not change the values of magnitude of the field. So it means that if I would use Cartesian coordinate system, I will have two variables, because due to x and y the field will change. With respect to z it will not change. Okay, if I'll use cylindrical coordinate system, I'll have one variable, because field will not change with respect to phi and z. If I use rectangular spherical coordinate system, the formula for electric field intensity will have two variables. So why make our life difficult by getting a formula which has two variables? Why not use a coordinate system which will which will give us the expression for electric field intensity, such that we will get only one variable. All right, so this is symmetry check clause 1. Clause 2 is that once we have chosen that we'll be working in this formula, in this coordinate system, so it means that now maximum we can have rho component, phi component and z component of field. Okay, so let's start deriving the formula of electric field intensity using cylindrical coordinate system. Okay, and then while driving we will do the symmetry check number 2. While driving the expression, we will see that which component of the field is expected to be present and which are expected to be absent. So that's it for today, and inshallah we'll explore it in the first lecture of the next week, inshallah. So till then, assalamu alaikum and fi amanillah.